Kalyan, I can see the screen. Yeah, it is live. It is live now.
Okay, I guess I'll get started. Welcome everyone. Welcome everyone to the webinar. Today's topic is data center security in the context of block storage. We have two industry veterans, Subhojit and Kedar, to talk about this topic. Subhojit is from IBM, working as STSM for IBM Storage Virtualized product. He has 20 plus years of experience, and he has worked with other big companies like Veritas, Brocade, and Semantic, and so on. He specializes in block storage architecture and storage networking. And to his credits, he has more than 100 patents issued. That's pretty awesome. Kedar is a solution architect working at IBM Storage Scale team. He focuses on container native storage, data caching, DR for highly scalable file and object storage solutions. So welcome everyone. Kedar, Subhojit, take it over.
Hey, thank you, Kalyan.
Thank you, Kalyan, for the introduction. So I'm here. Thanks for the opportunity, Sneha, and everyone else involved in this, and really grateful to be able to present this to this audience today. I have my colleague here, Kedar. I will be starting off with what really are the threats, kind of taking you through what is involved in building a secure block storage, and what are the criteria that need to be kept in mind while doing so. There are many aspects. We'll mainly go over the high level view of all these things, and then hand it over to Kedar, where he will talk about one of the most prevalent threats that we have today in any type of storage, which is ransomware. So let me just start the presentation here. Okay. It's a bit of a statistics here. This is a little old statistic. This is pertains to 2021. And what we all know, and a lot of us essentially know, both enterprise and individuals are subject to more and more cyber crimes over the years, and this trend is growing. And this here we actually see how enterprise block storage has been subject to cyber attacks. I wouldn't say enterprise block storage, but enterprise storage essentially. And the numbers are staggering. I mean, it's quite interesting that, and these numbers are growing. So this is kind of a 2-year-old slide. So these numbers would definitely be growing. And, we see that total cost of damages is something like roughly $6 trillion in these kind of breaches, data breaches and security breaches. And we kind of tend to see every 11 seconds a company becomes victim of a cyber attack of varied nature. It need not be ransomware, although that's the most prevalent one that we get to hear nowadays. And interestingly, some of these breaches really are because some very basic stuff is not taken care of. For example, data is not even encrypted. So 97% of information leaks, extracted data was not encrypted. Right? I mean, basics. The other interesting aspect to kind of think about here is that it takes about 280 days average amount of time to identify and contain a security breach. So what does it really mean? I mean, the security breach happens, it gets detected, and then finally once it's detected, it's blocked, and then there's a recovery process. If at all there is enough data to be recovered from, or secure data to be recovered from. And 280 days, I mean, that would essentially bring down organizations completely to their knees. So that's a huge number. And that's one of the reasons why most major enterprise block storage vendors have been focusing a lot, some of their efforts on how to secure storage at various levels. Of course, file storage vendors would be doing the same, but today's discussion is mostly centered around block storage. So let's move on to the next slide. Here, I mean, if you think about it, the real story about block storage connected over storage area network, a shared block storage connected over a storage area network, access through multiple hosts, uh, and those servers essentially are again accessed by applications over a client LAN. It's a multi-layer architecture generally in shared storage. And even if it is not shared storage, even if it's hyperconverged storage and stuff, there are multiple layers involved, and that makes the complexity of building a secure block storage higher. And security has to be applied at various layers for various aspects, and we are going to go through some of that stuff. Um, some of the threats that we can think about here, I mean, in yesteryears, malware threats like viruses and stuff were very prevalent. I mean, there were whole virus, I mean, companies essentially working to detect and monitor and recover from viruses. Um, but now the whole, I mean, a lot of focus has shifted to ransomware. What really does it do? We really hear so many cases of ransomware. Some may even have affected our individual lives. For instance, I know a particular case wherein the Garmin data centers were uh, compromised due to ransomware. And if you are a Garmin user, you know that you cannot upload your data onto Strava, and that causes a lot of pain to a lot of people in that community. So I mean, that's when I got aware of this thing, that it really does affect you. And the money that essentially these companies have been paying to uh, get back their data from these bad actors is staggering. um, then there are, I mean, of course, ransomware, while we hear a lot about it, there is also unauthorized accesses to your data, wherein people who are not authorized to access a particular type of data break in and kind of access that. So that kind of issue is, it could be within from within your organization or outside your organization. Data exfiltration is always a possibility. And then data interception. This is something where if your data is in flight, maybe you are doing a DR operation between site 1 and site 2, and you are sending your data over the public network or even a private network. There is a possibility, of course, if you have a private network which is completely secure, then that's a separate issue. But generally, you would, if you are sending data over hundreds of kilometers into the cloud, you would tend to use some part of the public network. And data interception essentially is possible, wherein an intruder comes in and picks up your data from the network if it's not secured or encrypted. So some examples of how block storage is threatened. Um, and on the right side, what really we have is um, scenarios which uh, threaten block storage not from the security angle, but from failure perspectives. So you can have uh, a disk failure, you can have a controller failure. Basically, your system has to be fault tolerant. This is something that has been there for a lot of time, and most enterprise storages essentially have these capabilities built in. They kind of account for hardware failure, they account for site failures by means of disaster recovery or high availability capabilities. And then, of course, data corruption can happen. I mean, if I'm transmitting my data from point A to point B, there may be elements or reasons in the path between that the data takes where data can get corrupted. Now, why are we really talking about these things which have been there for so long? The thing is, with these new threats that are showing up, some of these old paradigms that were there for preventing data corruption or hardware failure or fault tolerance for that matter, or site failures, they have to be enhanced and they have to account for data security now. So let's have a look at, this triad, the triad of data security, integrity, availability, and confidentiality. This has been there for a long time. We will see that there are standards that have evolved. NIST essentially is a standards body which kind of gives a holistic approach to data security. And the key point here is that when we want to secure our data, whether you want to authenticate, for to ensure that all these three aspects are taken care of, you have to join data security and data protection together and make them work with each other in tandem so that we have a complete solution. And again, when it comes to data security, what are you really doing? You are monitoring for malware, you are detecting malware, and you're probably blocking access to your storage if once issue is detected. What is authentication? You are essentially making sure that you are identifying, or the identity of the person who is accessing the data is verified. And there are many ways of doing these things. Um, Encryption is, there are various levels of encryption. We'll go over some of those, and you want to make sure that data is not accessible as clear text, and it's not very easy to break into, whether it's flowing over the network, stored on your data storage, or for any other reason. So that's essentially encryption. Authorization essentially deals with making sure that um, if you are talking about shared storage, for example, it means that not one but multiple people are accessing that storage, and you want to make sure that those who are authorized to take take certain actions from that particular storage are authorized, are allowed to do only those actions. You don't really allow an actor who is not authorized, for example, to delete some data, to go ahead and delete data or a snapshot for that matter. So it's basically authorizing the person in the right manner to ensure that once logged in, they can only do what they're allowed to do. And then audit logging. This is something that is absolutely mandatory because in the data center, so many activities are going on, and you have to make sure that all the actions are logged for future forensics. And I already talked about this, but data protection on the right side essentially is about data availability. So on the left, data security is more about data integrity and confidentiality. Data availability is dealt with by data protection, wherein you have various types of redundancy. You can have disaster recovery configurations. You can have high availability configurations between two near sites for instant failover and failback. You can have uh, fault tolerance like RAID and mirror and stuff within your storage controller. Of course, backup is a very key aspect, which essentially is necessary to make sure that older copies of data are saved, so that in case there is a data corruption, an older copy is available for use. And then error correction techniques. So if I'm transmitting data from point A to point B, then obviously I want to make sure that the data has reached, what I am sending is what has reached from point A to point B. And there are, if it has kind of got changed in the on the way, there is a way to detect it, and in a lot of scenarios to be able to auto correct that situation. But the key point here is that all of these things go hand in hand. And if you want to really have cyber resiliency, one must essentially take care of both aspects, data protection and data security. And data protection must evolve in certain ways from what used to be done earlier, so that it essentially gives a holistic solution. Um, NIST, I referred to this earlier, National Institute of Standards and Technologies. It's a body which kind of defines various aspects of how we identify the threat. I mean, in order to avoid or prevent the threat from kind of going and destroying your data, you must identify what that threat is. For example, it could be ransomware, or it could be unauthorized access, data exfiltration, or different types. You identify the threat. You then, so there are ways to identify threats, and then you protect your data from those threats. For example, if I want to protect my data from unauthorized access, I may want to encrypt my data with a certain key. Or if I want to make sure that an unauthorized access like a ransomware can encrypt my data, I want to keep copies of the data around. Or I may want to keep a air gapped copy on the cloud. So there are ways to protect my data. Detection essentially deals with how do I make sure, or how do I even know that a breach has happened? And there are ways and techniques to do that. Uh, Once the detection happens, we must respond to the threat, meaning that we probably block access for certain users or applications or servers, and probably even close down the data center. It could be physical in nature. And once we respond to the threat, we may have to, once we detect and then respond to the threat, we have to make sure that we bring back the data center as early as possible into its old state and reinstate the data back to the closest possible copy that is available, which essentially fulfills the requirements without being encrypted or corrupted. So essentially, if you see, I mean, why I have been talking about this thing is that data protection is primarily meant for recovery. So I mean, if I have fault tolerance, if I have a RAID storage or a mirror storage, it means that if one of the disks fails, I have another disk available to recover from. Or if I have a DR site 1 and site 2, between site 1 and site 2, if site 1 fails, then site 2 is available with that same data. So data protection is primarily about getting copies of the data from which to recover from. But it really doesn't detect or avoid an attack. It helps you build the copies. What is data security? These are the standards that essentially help you detect and prevent the attacks. And these also define techniques or standards by means of which strong security can be built into the data. But once we put them together, what we get is data resilience. This is the way to make sure that the whole data is uh, resilient to any type of attack, right? And NIST is a standards body which essentially defines a lot of these standards. For example, FIPS is a security standard which is a compliance requirement for many organizations now. And it is both at the application level and at the storage level. And there are many standards of authentication and encryption that are defined by FIPS, which if the storage controller must comply with, then it has to comply with all those standards. So it's kind of a holistic look at how to build cyber resilience. So let's look at the threat mitigation strategies for various types of attacks and various types of threats that are there to the data center today. I'll directly jump into host authentication protocols. I mean, block storage, we know that some of the key protocols that hosts use to access block storage are iSCSI, Fiber Channel Protocol, or NVMe-F, the recent past. Each of these standards essentially has built-in authentication standards and encryption of data in flight standards. EDIF is basically encryption of data in flight. So if you're sending data from the host to the storage over the storage area network, then you have to make sure that the data is encrypted. In case of iSCSI, which is a pretty old standard, there is a mechanism to essentially use username and password in a protocol called CHAP, essentially, which stands for Challenge Handshake Authentication Protocol, where your password is, so you're the initiator which is logging in into the target identifies itself by means of a username and a password, and the target authenticates itself, and the target can also authenticate itself with the host, application server. It's a two-way authentication process. um, and there are many hash keys and hash algorithms that can be used to encrypt the key while sending it over the wire. For instance, FIPS standards allows only SHA-2 and SHA-3 encryption standards for encrypting those um, passwords. Now, that's the authentication part of it. It ensures that the host that is going to access the particular block volume that the storage controller exposes is authorized to do so, or authenticates itself. And then once that authentication is done, data is sent back and forth between the initiator and the target. And uh, if you want to encrypt the data now, and it's pretty much becoming a requirement now, essentially, one can essentially use something called IPsec security to encrypt the data using keys, essentially between the initiator and the target. So IPsec is a capability which essentially encrypts the channel between two IP addresses, and it really doesn't care about which is the application which is sending the data. It will encrypt everything that is coming on that secure channel. So iSCSI is something that can take benefit of IPsec. Fiber channel protocol is a storage specific protocol. There is a standard called FCSP, Fiber Channel Security Protocol. This is still not so much in prevalence in the industry yet. Unlike and the reason being that fiber channel essentially is a very specific storage interconnect. So if a break-in happens, which is generally over Ethernet or IP, it is not necessarily that easy to actually go and break in into a fiber channel storage. I mean, one can always still do it, because if you've broken into a server and which has mounted a block storage which is connected over fiber channel, you can always go and override the data. But uh, breaching the fiber channel frames is not so simple. So that's why, as I said, it's not that prevalent yet in the industry, but there is a protocol available, and the fiber channel industry is taking strides in the direction wherein FCSP can be used to both authenticate and encrypt data when it's sent from the initiator to the target. Again, there are multiple protocols like RSA and IPsec like protocols and stuff like that, which essentially FCSP specifies for encryption of data in flight. But they're all essentially possible to do. And then jumping into NVMe over fabrics, this can be over fiber channel transport or RDMA transport or TCP transport. There's a new standard that has come in, which is basically named as DH-HMAC CHAP. It's very similar to iSCSI's CHAP protocol, except that it is an enhanced version of it. It essentially uses Diffie-Hellman algorithm for sharing keys between the initiator and the target for authentication. It's more stronger authentication than CHAP, and that's the authentication standard for NVMe-F. And the target, you can, it also essentially allows you to use TLS 1.3 protocol for encrypting data from the initiator and sending it to the target. One can also use IPsec, as I said, because if you encrypt the channel between the initiator and target using IPsec security, any data flowing across that channel gets the benefit of IPsec security. This is one aspect of data path authentication to access the data's block storage controller, and one must take care of some of these things. Now, there are complexities associated with these, which we will get into in another slide. Um, Data confidentiality, again, this is something, how do I store my data so that it's not available in its open form to everyone? One aspect of it I already talked about is encryption of data in flight. I just talked about the various host attached protocols and how one can encrypt data in flight using those protocols. One interesting challenge that comes up here is that if the data is encrypted on the initiator using encryption techniques that are supported or prescribed by NIST standards, then data deduplication becomes practically impossible on the storage controller, because the same block essentially from the initiator, uh, once encrypted and once it comes to the storage controller, they're different. So you cannot deduplicate that data. So that's a challenge essentially with this encryption of data in flight. So a lot of storage controllers, what they do is they decrypt the data and then re-encrypt it while going for encryption of data at rest. What does it really mean? Data at rest is the data that is sitting on your drives. It could be NVMe drive or it could be a SAS drive. And again, I mean, you could use various techniques to encrypt your data at rest. It could be software based encryption, hardware based encryption, and nowadays we have advanced self encrypting drives as well. In fact, computational storage, one aspect of computational storage one could think about is utilizing the computational power on this drives to be able to encrypt the storage and or compress the storage and keep it. In fact, there's been quite a bit of work we've been doing in IBM on that aspect of uh, computational storage. Um, I mean, again, there are costs associated with this and complexities as well, because if you use software-based encryption, then one is subject to. I mean, it's expensive in terms of latency and where. I mean, do you want to encrypt inline? Do you want to encrypt offline data? Those are aspects that one has to kind of deal with while designing such a system. Uh, or one could use hardware-based encryption as well. I mean, there are some of our processors nowadays give faster instructions to encrypt data. Those can be used, or there are specialized processors. Some of the adapters, host adapters, essentially allow encryption offload. Those can be used to make sure that encryption of data at rest is essentially utilizing hardware encryption capabilities to do the job faster. What is secure erase of data? Secure erase of data is to ensure that if your system is being decommissioned, or maybe if a shared system is used by multiple tenants, then once the system is decommissioned, uh, one can essentially make sure that the data that was stored by that particular tenant, or before decommissioning of that system, whatever data was stored on the drives is destroyed. Because it's always possible for someone, if it's not destroyed, to actually retrieve that data and misuse it. Interesting aspect of this is that there are multiple ways of doing secure erase of data on block storage. Most drives support it, and some of them are expensive, some of them are more quicker and to essentially kind of execute. For example, if you can overwrite the data with zeros, or you can overwrite the data with ones, and SCSI supports the sanitize command with various options. Now, the most interesting aspect is the cryptographic erase option of sanitize, wherein instead of actually overwriting the data, which takes a lot of time and has complexities because of garbage collection issues and stuff like that in various drives like NVMe, uh, what you can really do is you keep the data encrypted and then just throw away the key, so that the data can never be accessed again once the drive is decommissioned or a tenant leaves the system, essentially. Data integrity, again, I mean, just running through quickly what are the options here. If and when you're accessing block storage, you are accessing block storage either over Ethernet or over fiber channel. These are two most prevalent techniques. I mean, one can use other transports as well, like InfiniBand, but I'm basically talking about the most common ones. And most physical layer transport protocols and transport protocols essentially have built-in capabilities to uh, provide data integrity. And what does this do? It says, like, if I want to send a frame of data from point A to point B, there is a possibility that due to any reason, I mean, due to electrical disturbances, or due to packet corruption or something, you essentially end up getting the frame which is changed at the target side. How do you know that what was sent on point A is the same as what you received at point B? And a lot of these physical layer protocols essentially implement data integrity standards. One of them is forward error correction techniques. All our optical transceivers today, like 10 gig, 25 gig, uh, that are essentially used to transmit both fiber channel and Ethernet frames, and the switching equipment, they all implement FEC standards. There are multiple ways. There are different FEC standards as well, and there has to be a compatibility between the switch port and the uh, storage and initiator ports so that this whole thing works together. CRC is pretty old stuff where you have cyclic redundancy check payload in every frame that is transmitted from the initiator to the target. This a little bit naive now because this while it just provides data integrity, but message authentication code mentioned at the end of this list actually is more stronger, wherein essentially there's a cryptographic hash of the payload that is calculated and put at the end of every frame. And it kind of makes sure that if the frame is changed by someone who is unauthorized, they cannot generate the cryptographic hash unless they have the key with them. So this is more secure and is used by protocols like IPsec, TLS, etc. And sequence counters basically make sure that your frames are reaching in order. Eventually, when the initiator sends frames to the targets over the SAN, you have to make sure that the data gets reconstructed on the target side as it was sent on the initiator. So that's about data integrity. It's not that this is a comprehensive list, but gives you an idea of what essentially is involved in data integrity. Okay, so authentication and authorization management path. I was so far talking about the data path. The important aspects are role-based access control, tenancy segregation, multi-factor authentication, multi-person integrity, and audit logging. Now, let's quickly go through each one of these. Role-based access control essentially means that when you define users of the storage, certain users are grouped into roles and they are only authorized to do certain actions. So for example, if you take a storage controller and there is a pool of drives, only the storage admin gets the authority to create a child pool and assign it to a tenant. But once the child, this is not available to the tenant admin, who essentially uses the child pool, but he cannot change the characteristics of the child pool. An example of role-based access control. And I'm sure Kedar will kind of allude to a lot more when he talks about immutable data copies for ransomware on role-based access control. What is tenancy segregation? It really deals with if I have my piece of hardware, my storage controller, being shared by uh, multiple clients, multiple tenants. What I really want to do is I want to make sure that each one is isolated and is not able to see the others configurations on the storage controller. So for example, if my storage controller is shared between two entities, let's say tenant 1 and tenant 2, if tenant 1 creates volume 1 and volume 2 on their pool of storage, and tenant 2 creates volume 3 and volume 4, tenant 1 can only see and manipulate volume 1 and volume 2. Tenant 2 can only see volume 3 and volume 4. This kind of tenant segregation, an example of uh, showing only their objects or storage objects to that particular tenant. And there are many aspects of storage and segregation, which in itself can be a topic of a full discussion, but I'm going to leave it at that here. Multi-factor authentication is basically having multiple. So, we know this OTP based authentication. Once I log into the system, uh, as using my username and password, that's one factor. And then there is a second factor associated with the login, where the authentication has to be done by another third party or a different application. It could be your mobile phone via OTP, or some other application like IBM. In IBM, we have IBM Verify, which is a mechanism to essentially authenticate the transaction, so that there are two entities which must be compromised if one has to essentially go and breach the authentication for a particular system. It makes it more difficult. What is 2% integrity? 2% integrity really means is, suppose I have created data copies, snapshots, right? And I want to, and they're immutable data copies, which means that they're very valuable to me when there is a ransomware attack. I only want some privileged users to be able to delete those data copies. Now, if I give that authentication to a particular type of administrator, it means that the moment that username and the username and password for that particular administrator is compromised, the system is compromised, and then the administrator can log in and delete those immutable data copies. So here what we really are talking about is that not a single person but multiple people must be involved in authenticating a particular risky action. It's very much like your bank locker example, wherein if you go to the bank locker, your bank has one key and you have one key and both are used to open the locker. So here, in a 2% integrity kind of implementation, one has to ensure that not only does one person essentially log in and is able to do risky actions, someone else is involved in elevating the authorization of that person to be able to do that risky action, to perform that risky action. By itself, the person who cannot just log in and delete a particular snapshot, for example. So that's 2% integrity, and audit logging is well understood. I mean, we essentially log every action of the administrator and the users to ensure that these are available for forensics later on regarding data breaches and what other actions users may have done. Finally, jumping into secure boot. Now, what is this? Essentially, secure boot is a method to ensure that the firmware or the bootloader or BIOS that you are essentially using on your storage controller is certified by the vendor, who is essentially it's authentic and certified by the vendor who has sold you that product, right? And it is not tampered. And there are various, it's a chain of trust kind of a mechanism where you have a trusted platform module which uh, which essentially authenticates certain hash keys for the BIOS, the bootloader, and the kernel, one in turn, so that finally when the application started, the TPM module gives access to that particular key to start that application. Now, why is this needed? It's needed because it is always possible for a bad actor to go and change the application that essentially is running on your storage controller and try to pilfer data. If one tries to do that, they will also have to make sure that the keys, which are essentially in the TPM module, are generated. And unless they have the encryption key, they will not be able to generate uh, that particular key, hash key, which the TPM module requires to let the system start. So secure boot essentially ensures that right from the beginning, when you're starting your storage application, it's from an authenticated source. I think I'm doing reasonably okay with the time. Kedar, I think I'll hand it over to you now. Oops. Okay. So I have one more slide here. So I have talked about a lot of these things, but what I really want to emphasize here is, for instance, I mean, what data resiliency we had earlier. For example, you can create snapshot images for backup. So if the data is lost, you can restore from a particular point in time. But now what you really need in the presence of these kind of threats is that you may want to create air-gapped copies of that data, or you may want to create lot more copies of the data than you used to do earlier. So your data protection techniques have also got to change. It puts higher requirements on the scalability of the system. There must be more snapshots supported. There must be more bitmaps for those snapshots. There must be space for those bitmaps. Similarly, if you were doing disaster recovery, for example, and you were doing snapshot-based disaster recovery, uh, you would essentially do a cycle of data and then delete the snapshot after that cycle from the suppose you're doing a snapshot based recovery. You are essentially going to keep the snapshot on the target site only for as long as the cycle is ongoing, and then once the syncing is over, you would delete that copy. But now you may need to keep that copy, because you need to keep those copies stored remotely for later recovery purposes, which may not have been required earlier. These are probably air gapped copies that you really want. So, and in addition, we have talked about a lot of encryption and authentication and stuff. All of those things were done very minimally earlier, but now with the addition of this security threat models in there, a lot more complexity comes in. And with that complexity, of course, one has to also balance the administrative difficulties that are associated with managing keys, keeping the data consistent and stuff like that. So I think from this point on, Kedar, um, please take over and uh, talk about ransomware, which is probably the most biggest threat today in the data center.
Sure. Hey, thanks, Subhojit. Thanks for that detail about how you can, what are the techniques where you can prevent the ransomware or prevent any events from happening in your to your block storages. And but at the same time, I think if we look at NIST infrastructure, if we look at that, then we're going to talk about it. But before we jump there, as Subhojit said, ransomware is one of the most uh, prevalent kind of malware that nowadays we run into. And ransomware, typically, if you look at it, what ransomware have been doing is once as part of infecting your data, they typically go and encrypt your data, basically encrypt your data so that and prevent the user of that data to getting access from that. And one of the techniques for that could be encryption. There could be other techniques. But the other interesting part that I was also reading about the ransomwares is nowadays ransomware, they also understand that a way to protect your data is to kind of take copies of your data and so on. And so ransomware are actually becoming smarter and to see that whether they can actually make those copies of the data unusable, right? And uh, at the end of it, basically, as Subhojit showed in on the first chart, that they are going to ask for money from you in order to kind of give you ability to get your data back. So either then you are kind of stuck in either giving the money or kind of stuck in doing a long recovery from the ransomware. So I think prevention is always the best technique. But no matter what, if no matter what sort of prevention you're going to put together, the ransomware guys who are developing it, they are probably a step ahead, and hence following the NIST infrastructure, right? And that becomes very important. Which is first step of that is really protect your data. Now, block storages have been providing data protection or techniques to protect your data from ages, right? Since they started, and snapshot has been a very common technique for that. That if you have a logical corruption of your data, now in this traditionally it was done to kind of uh, avoid errors by the users and so on. That if you want to recover from those errors by the users, then the easier way is that you have a take a snapshot, and then once you detect such errors, then you can recover from the snapshot. uh, and then there are different types of snapshot. That of course you have writable snapshots and you have read only snapshot. But the more important part when it comes to ransomware is uh, it's not sufficient to just create that read only snapshot, because as I said, the ransomware are getting smarter, and they may some either the ransomware itself will go and try to delete these snapshots, or there may be a user admin who doesn't know why these snapshots were created, and they might delete in order to create some space. And so that's where this whole immutable snapshot concept came up, that the way to avoid any of the errors is to create the immutable snapshot. So that two things that happen: one is uh, one is the data cannot be changed on these snapshots. So there are more or less like a read-only snapshot. But the other important aspect of it is you have to, as a block storage, you have to also make sure that those snapshots themselves cannot get deleted, right? And that's why they're kind of talked about as immutable snapshots. So the immutable snapshots are the ones that get created, and then they come up, and when they are created with an expiry date for that snapshot, and no one can actually go and change that or delete that snapshot before the that date shows up. And at that point, those snapshots would be kind of deleted on its own by the storage system. Uh, but while we say that, I think Subhojit alluded to the two-person authorization, and that becomes very important from when it comes to immutable snapshot, that you have a separation of duties between the users who are going to create the snapshot, and if there is a need for whatever reason to delete these snapshots, the expectation is in most of the cases these snapshots would get deleted automatically once the retention period is over. But at the same time, I think there is always a need that there is a need to delete such immutable snapshots, and the only way you need to allow that to happen on your system is by having this separation of duties. So as the picture shows, that you have an administrator on the left hand side who's doing day-to-day tasks, and they are the ones who are setting up the immutable snapshots, so that these immutable snapshots uh, are taken at a scheduled intervals. And while that schedule can be controlled by the administrator, once that schedule is set up along with the retention period, then that administrator cannot himself or herself cannot go and delete that snapshot. And the only way to do anything to those snapshot, now if that person cannot go, administrator cannot go to another administrator and say, can you delete it for me? I think if you need to then define different users in your data, in your basically amongst the users who are able to control the storage, as security administrator and super user. And unless both of these roles, or someone who has these roles, authorize that deletion of immutable data copy, that deletion will not happen. And that's where the immutability concept comes in, that not only the data cannot be changed, but it cannot be uh, deleted as well. The other aspect of it, just going back to the prior slide, I think it's important to have automation in place where these data copies or these immutable copies can be instantiated at a scheduled time, right? And this can be daily, this could be every 1 hour. So depending on the importance of the data, and depending on how you want to protect that data, all these policy and the amount of storage, the impact these copies creating so many copies can create to the overall performance, are some of the factors that you would decide what's going to be the schedule at which you're going to create these copies. But the important aspect of is uh, having an automation in place where these copies can be easily created. At the same time, when the copies can be easily created, it's also important to have a automation around the restore of the copies, and that's what we'll talk about. That other than the creation of the copies, if you look at again the NIST infrastructure, the some of the next steps in the NIST infrastructure are detect, then basically react, and as well as and then recover, right? Or so in order to kind of integrate all these steps, if you look at, there are two ways to do it. Either you can actually try to build these steps by yourself, but this overall market, if you look at it, the storage and security have sort of come together and converged. And in the security, from the security side of it, there is already basically security information and event management systems that have got developed in terms of in terms of detection of these cyber security threats, in terms of creating log aggregation, creating analysis of whatever is available, as well as correlation between events and given that the security information and event management systems, or also known as CM systems, that are already available, I think it becomes much easier for any storage to go ahead and integrate with such CM systems from an automation perspective. And when we talk about the such integration, what's important is uh, from a detection perspective, where can storage help? So traditionally, again, if you look at malware or ransomware detection, uh, most of these detections are done in memory based on certain patterns of the data. But where the storage can help here is uh, a storage system knows that what is the workload pattern, right? It knows in terms of read write patterns, it knows in terms of what blocks are getting modified, it knows in terms of whether each block that is getting modified has a similar size and across the storage system. So given that all such different patterns are known to the storage system, it's much easier that detect once such patterns are detected, storage system, block storage system can, as part of the integration, can set that when certain workload patterns show up, they can say that this could be this particular pattern may be a malware, and maybe because of a malware, and hence go ahead and take the required actions, right? And uh, so just a sec. Subhojit, are you able to hear me?
Yes, I can hear you.
I seem to have some issue with the slide change. If you could move the chart forward for me.
Yeah, sure, I will do that. Oops.
Are you able to move it?
Yeah, are you able to see the slides?
No, just probably some issue on my end. Just let me know if you are on chart 19. I'll go ahead and talk about it.
I am on chart 90. There's the workflow here.
Okay. So yeah, if just give me a minute to pull charts locally on my desk.
Until then, I think, Subhajit, you can answer a question that's come up from Naveen Habu. Uh, he's asking, what is the difference between MFA and TPI?
Yeah, thanks for the question, Naveen. I think multi-factor authentication MFA is really to use two different authentication methods to authenticate a single person. Whereas two-person integrity is ensuring that not a single person is authorized to do a particular task, but two people are authorized to do the task together. So, for example, if suppose, one way to do things is you have this immutable data copy which needs to be deleted now for some reason before its expiry, and the security admin logs in using his username and password, and since he is authorized to do this operation, he deletes it. Now, you don't want that to happen. Therefore, what you make sure is that if the single user who logs in to delete that particular um, snapshot is not able to do it until another person elevates the privileges of this particular user so that he can do it, which means that if I am a security admin, I just cannot log in and delete the snapshot. Kedar, who is another security admin, has to elevate my privileges before I can perform that task. It means that two people have to be compromised before you can essentially breach that security and delete a particular immutable data copy.
Sure. Thanks, Subhojit. So yeah, I'm on the next chart, which shows how you can integrate with the CM server, right? And what you have at the bottom is really a block storage system which has enabled various sort of audit logs, and these could be audit logs based on the who's accessing it or what host paths are accessing it. These could be audit logs based on what data is getting accessed and so on, right? So audit logs can be of various types. What it's showing that a storage system, how it can integrate with the CM server is it can basically share these audit logs that a storage system is collecting more in real time with the CM server, right? And once these audit logs are shared with the CM servers, in the CM server, it will map the it's going to do analysis of those audit logs and map these storage events to various CM identifiers. The other part that would have happened earlier is as a block storage system or as a storage system in the CM server, a security administrator would have configured a set of rules and alerts, right, for the threat detection. Uh, so uh, basically, what is happening in steps 1 to 3 is the storage system is basically in real time providing data about its workload to the CM server. As step of as step 5, which happened earlier, that the CM server has already been configured that what sort of workloads, what sort of data patterns need to be kind of alerted as threats or need to be and once that those threats are detected, then an automated actions are already created on the threat detection, right? So as part of step 6, what will happen is that once the threat is detected, it will automatically invoke a workflow on the storage system. The storage system can go ahead and then at that point take a say a immutable snapshot which is very close to the time when the detection happened. So, of course, it could be past the event, but at least it is very close to the event. And then you know that this immutable snapshot got triggered after just after the event was detected. And that may still be a good time because it's possible that the few of your or some part of your data has got basically affected, but the large part of your data is still not got affected. So taking a immutable snapshot at that point in time is still a good thing to do, and that's what you can automate. As part of protection, you were anyway doing immutable snapshots at a given interval, and here by integrating with the CM server, you can actually take another snapshot just after the event got detected. So once the event gets detected and a snapshot gets created, then the next part of the automation is really the recovery. And it's important to do this automation either in the block storage itself or by integrating CM servers. So that because if this happens in the middle of the night, you want all this workload to be triggered automatically rather than waiting for admin to take some actions. And which can happen much later, say, and you will lose an important basically time if you keep all these actions on the admin rather than automating these actions. So as part of the overall cybersecurity, I think the block storage just providing all these automated actions and integrating with CM server becomes very important. The other aspect of it that a lot of times I think when we talk about uh, the block storages or storage that you will get asked questions around that are you kind of compliant with a particular standard, and I just wanted to quickly list out the standards that are important from any storage perspective and that one needs to kind of comply to from security perspective. Of course, the first one we have been talking, the NIST CSF, something that we have been talking earlier, but also standards like GDPR, HIPAA, and they've been around for a while. They become important as well. So I think in conclusion, uh, we've been kind of talking through around this framework. These are the different steps: the identify, protect, detect, respond and recover. These are the important steps in this framework. And we sort of touched upon these various steps, as well as the actions that a block storage can take to become a secure block storage, as you provide the block storage to various data centers. So that was our final chart. I think if Preetham, if there are other questions, we can probably take it at this point.
Yes, Kedar. So there is a question from Vidushi Mishra from IBM. She's asking, would there be a performance challenges with the different encryption? What are they, and how much drop should be acceptable?
So I will take that, Kedar. So I mean, see, at IBM we have something called flash core modules, where the inline encryption performance drop is zero. Essentially, there is absolutely no performance drop. It's performed in hardware, so that's a unique capability that we have in that drive. But there are other techniques, like I said. I mean, if you use software encryption, then there is a significant delay in latency that can be observed. We in fact were not able to go beyond like maybe about 50% of the available bandwidth, in some cases 20% of the available bandwidth. So software encryption in most circumstances could be, I mean, very high latency and it can drop bandwidth. But then again, at the end of the day, you have to decide what is more important for you. Software encryption can always be cheaper, and then, of course, somewhere in the middle lies the capability to use off-thread adapter encryption capability for this purpose, which will probably perform somewhere between self-encrypting drives like the one that I mentioned and software encryption. So that those are kind of the kind of latencies and drops that you could see with different techniques of encryption.
And Subhojit, one of the interesting ones nowadays is, of course, while the SED drives are getting more common, I think in a multi-tenancy type of case, uh, it also becomes important that you use software encryption, because if you want different types of encryption that are being used, depending on which host path the writes are coming from or the updates are coming from, or where that workload is running in different encryptions for different hosts. If that is required, then there is still a need for software side encryption.
Yeah, by the way, the talk is going to end. I think we have gone over, but we'll be very happy to answer any questions later. Pritham?
Yes. So anybody who wants to ask more questions to Kedar and Subhojit can kindly drop your questions to the email address sneha.india@sneha.org. So we will take it up and respond back to you in time. Yes. So Kalyan, I think we can close the
Okay,
talk for today.
thanks everyone for joining, and thanks Kedar, Subhajit, for wonderful session. Um, for the audience, look out for another email in a week or so for the next webinar.
And
Thank
thanks, Sneha, for giving us the opportunity to present this today.
Yeah, thank
Thanks,
you.
thanks
Thank
a
you,
lot,
everyone.
Subhojit and Kedar. It was a great
Thanks to
session.
all the audience. Thank you. Bye bye.
Thanks.